I was really excited about the excellent lineup of speakers, and I'm happy to be part of it this semester. Today we'll be interested in design of decentralized strategic learning algorithms for network multi-agent systems with uncertainty. And what do I mean by this? Traditionally, strategic learning or game theoretical learning refers to a set of simple decision-making rules for players in the game to follow, so with the hope that upon execution that these simple decision-making rules will converge to an optimal operating point of a game, which I'll broadly refer to as equilibrium at this point. The algorithms we design in this talk, or we will be talking about, will be tailored to network systems with uncertainty, which means that agents will, or players will have some payoffs that are that depend on the actions of other agents in the system. And also they'll have some uncertainty about the payoff relevant parameter, or so some of the unknown payoff relevant parameters will be unknown. So the algorithms we design will not only abide by the limited access of agents to information in network systems, but also be mindful of the possible costs of information exchange among agents. So just to begin, network systems are everywhere. They appear as communication networks in transportation systems with unmanned vehicles, in search and rescue missions held by a team of agents, or in swarms. As we all now know, infectious diseases in a population spread via contact among the susceptible individuals and the infectious individuals, hence they can be considered a network system. The electricity grid is a canonical example of a network system that is designed to transmit energy to consumers, from supply to consumers reliably and efficiently. And all of the systems, these network systems, which I have named here as autonomous robots, epidemics, and energy systems, will contain multiple interlinked decision makers whose individual actions have consequences on the performance of the overall system. So modeling and designing decentralized decision-making in each one of these areas is an active research direction that contributes to the vision of each domain. So in this talk, we'll focus mostly on autonomous teams, autonomous robots. So I'd like to go over the vision for this system. So we managed to build robots that scale from centimeters to meters with varying capabilities, and we managed to put these robots in a wide variety of objectives in teams to achieve a wide variety of objectives such as active sensing, containment, surveillance, and shape formation, as you see in this video of 1,000 robots forming 2D shapes. But the vision is that these robots should be able to plan, learn, and coordinate in novel environments, unlike the one you see in the video where it's an isolated environment. So there lies certain challenges that we need to overcome to attain the vision highlighted here. So when we place these robots in novel environments, the information about the given task will be inaccurate and dispersed. So agents will have different information about the task given, and they will need to think about what others are thinking about the task given. Moreover, agents may lack the ability to get a global view of the team behavior as they gather information about the task, since they may only be able to interact with only a subset of the agents in the system, as I show here in this, as I describe here in this video, in this simple picture. In such settings, really reasoning tractably about best behavior based on local information may not be possible. So the challenge that agents need to rely on partial information to reason about the information and goals of other agents in the system is common to all network multi-agent systems with uncertainty. So in this talk, after providing a formal definition of what I mean by network multi-agent systems from the perspective of Bayesian network games, I'll provide some simple, some older results on theoretical results on convergence of rational behavior. Then we'll switch to a particular class of bounded rational algorithms which I'll call as decentralized fictitious display. That's what the FP here refers to. And then we'll generalize these algorithms to include voluntary communication and to their performance. We'll try to characterize their performance in unknown environments. Okay, so just to be formal about slightly more formal about the stage. So we're going to represent the agents as nodes in the graph, and their connections in a graph will represent possible information exchange between agents. So agent 1 here has neighbors 2, 3, 7, and 8, and we'll denote the neighborhood of agent 1 with n parentheses 1. Here you can see 2, 3, 7, and 8 are the neighbors. Here I'm showing obviously a static network, but will allow the network to be time varying and be connected over time. And we'll be more formal about it. And we'll also focus on random graphs, so the information flow can be faulty or can fail. Okay. There will be an environment that I'll represent by theta, and this will be unknown to agents, and agents can receive possibly some signal about this environment at each point in time or once, and this signal will be noisy, and this could be an additive noise or some other noise. So we'll be interested in repeated decision making of agents. So I'm going to denote the action of agent 1 at time t by a1t. And agents are going to act with respect to their objectives or payoffs, and their payoffs are going to be denoted by u. So agent 1's payoff here is going to be denoted by u1, which depends on its own action, a1t, actions of others, and the environment variable. So a minus 1t here represents the set of actions of all agents, all other agents in the system, and theta is the payoff relevant parameter that is unknown. Okay, so after making decisions, agents at each point in time can receive messages from their neighbors. So I'm going to denote the message that agent 2 sends to agent 1 as m2t, and then so on. And so agent 1 here can receive messages m3t, m7t, and m8t from its neighbors. So then the information of agent 1 at time t plus 1 is the previous information it had, the signal it received at time t, and the messages it received from its neighbors. So here the messages are denoted with n1, n parentheses 1t, and the information of agent 1 at time t is i1t, and the left is the information of agent 1 at time t plus 1. So what's a reasonable thing to do for agent 1 once it has this information at time t plus 1 is to take the action that would maximize its expected utility given it all of its information. This would be easy to do if agent 1 had an idea of what other agents are going to do. So the problem here is a1 minus 1t plus 1, where other agents have potentially different information because they have different neighbors and they have different information about the environment. So agent 1 has to think strategically about the motives of other agents based on its own information. So in a sense, agent 1 has to model what other agents are going to do. So so we're going to use game theory to formally define what's a rational or best possible way an agent can do this in this setup. And game theory is, as you may be all familiar with, is concerned with decision making of self-interested individuals. So here we have agent 1's information, and all other agents have different information, obviously. We're going to define this notion of strategy, which is a mapping from any information that agent 1 can have to the set of actions, possible actions. So you can think of strategy as a book where each page of the book corresponds to an information, and in that page you see the action or the playbook, you see the action that agent 1 has to play. So the strategy profile of all agents will be captured by the sigma, shown here in red, and this is the strategy of all agents across all times. Okay, so a strategy could be just play action A, regardless of the information you play. That's a valid strategy. In the playbook, all the pages will show you A. Okay, of course, we're interested in a bit more involved strategies that are rational. So notice that agents have different information, but given that they know the strategy, the book that other agents have, or the playbook that other agents have, they may reason about the information of others based on local information and the strategy profile sigma. Okay, so so how will they reason? They need to put beliefs on what has happened. So they need to put beliefs on the history of play. So what do I mean by that? For that, I need to define the space of plays, omega here, which is basically the set of possible environment values, theta, and the possible set of signals and actions that can happen across over time. So suppose agents have some prior P on the environment and the signals that may be revealed to all the agents in the system. Together with the strategy profile sigma, this is going to induce a distribution on the space of play. So given this prior on the space of play or the history, agents belief is the conditional distribution with respect to this prior, given its information. Okay. So given this belief definition, a strategy profile is a Bayesian Nash equilibrium, or here I denote it by sigma star, if it satisfies this inequality shown here. And the left-hand side of the inequality is the expected utility of agent I, given that all agents play with respect to the Nash equilibrium or Bayesian Nash equilibrium strategy profile, sigma star. The right-hand side is the expected utility of agent I if it deviates to another strategy or another action unilaterally, while all other agents stick to their previous to the strategy, Nash equilibrium strategy profile. Okay, so the left-hand side is always greater than or equal to right-hand side in a Bayesian Nash equilibrium setting. And so the Bayesian Nash equilibrium strategy is optimal with respect to strategies of other agents given local information. Okay. Notice that there needs to be some consistency between the way we form beliefs and the way we compute our strategies, because our strategies induce beliefs and our beliefs are used to evaluate the strategies that we play with respect to. Okay. So just to set this in a block diagram format, just to illustrate what's going on. So at time 2, agent I may have its information II2, which is its signal, its prior, and the messages it received from its neighbors. It's going to process this information, assuming that other agents follow some strategy, the optimal strategy profile, so it can form expectations. Using this, it can take the best action possible or strategy possible, which is going to lead to an action. And all agents are going to do the same thing in each step. And then that information is going to be filtered through the network. So agent 1 can receive information from 2, 3, 7, and 8. And the process is going to continue like this. So this process I define as Bayesian network games. So a natural question one can ask is, what happens when individuals act according to their optimal strategy at each step? And we answer this question for the particular class of games, which I'll label as coordination game. So the coordination game, I'm going to describe it in the context of autonomous teams, but you can generalize it. So the idea is, suppose these robots are given a true heading direction, but they receive noisy information about this. So they would like to, over time, find the true heading direction while avoiding hitting each other. So they don't want to, they want to move in the same direction as well as estimate the best heading direction. So given this setup, we have this result that says that if agents are playing this kind of coordination game and only observing the actions of their neighbors, then they will reach consensus over time. So they'll heading directions will align. So they'll move in the same direction, right? And moreover, their expectations about the environment, the true heading direction, will align as well. Okay, so the second part of this result says that not only that, but just by observing the actions of their neighbors, agents are going to be able to aggregate information. So an agent I's expectation of the environment given its local information will equal to the expectation of the environment given all the information available in the system. Okay, so you can find actually counterexamples of games, coordination games, where this doesn't likely happen. So you can construct signals where this doesn't really happen, but these are non-generic examples, and this result holds generically. Okay, so this result generalizes. It's an old result that we have that generalizes social learning results, Bayesian social learning results to games where agents' payoffs depend on each other's actions. Okay, so asymptotics are good, but can agents compute the rational behavior or Bayesian actions rationally or tractably? And in general, the answer to this question is no. So it makes sense to think of, from design perspective, to consider bounded rational actions that are simple to compute, or simple decision-making rules that we hope to converge to rational behavior over time. So here we'll focus on a particular algorithm within the class of best response type algorithms, which I'll refer to as decentralized fictitious play. And we'll talk about different generalizations of this, but let me introduce decentralized fictitious play in this simple example first. And this example is the task assignment problem, where we have 5 robots here and 5 targets, and the objective is, global objective of the team is to cover all targets with minimum effort, which can be represented by this payoff function, where agent I receives a payoff of 0 if it selects target T and another person is selecting target T. It receives a payoff, positive payoff, inversely proportional to the distance it has to traverse to get to that target if no one else is selecting that target T. Okay, so here the distance is denoted by the distance between the target it selects and the point, the current point of agent 3 or agent I is denoted by xi, and theta t is the location of target T. And we assume these targets are unknown to agents at the beginning, and agents can receive noisy information about these locations. So agents have different perspectives on what the payoffs are from different targets. So this problem has been studied in the context of controls and robotics from different perspectives, path planning. Here we'll be only interested in scheduling of agents to targets. Okay, so I'm going to provide a simple intuitive decision-making rule, and then I'll describe the algorithm in more detail after this. And I'm going to describe this algorithm, local algorithm, from the perspective of agent 3 at location x3 with neighbors 4 and 5, receiving information from neighbors 4 and 5. And moreover, agent 3 here may have noisy information that's about the locations of targets, and that's this represented by this oval around T4. So agents are going to start with, agent 3 is going to start with estimating congestion at each target. Suppose agent 3 was thinking that previously all targets are selected by one individual, so all targets are covered. It's going to subtract the congestion caused by itself. So previously, suppose agent 3 selected target T4, so it's going to subtract the congestion caused by itself. Now it's going to compute the expected utility from each target. Obviously, because other targets are, agent 3 thinks that other targets are selected by other agents, it's going to pick target T4 because that's the one only giving, that's the only target that's giving a positive payoff. It's going to pick that target. It's going to move in this direction, and all agents are going to go through the same process in the time being, and they're going to pick their selected targets and move in the direction. Now, agent 3 is going to update the congestion caused at each target because it selected T4. It updates it and says that, well, target T4 is selected by me. It's going to share the congestion estimates with its neighbors, receive information from its neighbors. And this information, based on this information, agent 3 is going to update its congestion estimate. Suppose agent 4 also selected target T4. It's going to learn about this in this step. And once it learns about it, it's going to update the congestion at target T4 to 1 plus alpha. And it can also receive signals about where these targets are. So the uncertainty around the target locations may shrink as well. And then the process, we go back to step 2, and then the process repeats. So these 10 steps can be actually simplified to 3 actually in algorithm format, but this is how agents can play out in 10 steps, and this algorithm I'll denote as decentralized fictitious play. And before I describe this algorithm in more formal way, let's see how this algorithm plays out in the task assignment problem. To set the stage, here we have 5 robots, 5 targets as before. Agents receive independent signals about target locations, which are denoted by these pink circles. So what you see is that agents on the left, these 2 robots, wheeled robots, are going to the same upper left target, but then this robot decides, well, this target is being selected by someone else, so it's going to go to the other target at the bottom left. Okay, so and then they circle around because they learn more about the target locations, and then they'll eventually end up at the target. Okay, so there are 2 caveats to this algorithm. First, we have a fixed underlying communication network. So all agents attempt to communicate with each other all the time. and there's a constant and the communication attempt, and these attempts are successful at each point. Okay, so so what is the algorithm that agents are playing with respect to? We can define this in standard fictitious play, not the decentralized version. With inertia, agents assume other agents use stationary strategies that come from their past histogram of actions. So I denote, so this assumption is not true, right? That's why it's bound rational, but agents model as if other agents are playing with respect to their past empirical frequency of their past actions. So I'm going to denote the empirical frequency of past action of agent J with FJT. So this is a vector, it's a distribution on the action space. And this is updated with respect to some loss of memory plus the new action that comes in weighted by a fading constant alpha. And this alpha could be 1 over t, then agents equally weight every action that is being played. So it's an actual averaging of all the past actions. Or it could be a constant between 0 and 1. So given this empirical frequency, assuming others follow this empirical frequency, agent I can compute its expected utility by just plugging in f minus it to this utility function evaluation. And this is how I will denote the expected utility of agent I given at time t. Okay, so given this expectation computation, agents are going to best respond with inertia. What does that mean? They're going to pick the action that maximizes this expected utility with some probability 1 minus rho. With probability rho, they're going to stick to their previous actions and they're going to continue what they were doing from the past time. Okay, so let's come to decentralized fictitious play. Well, in decentralized settings, state and empirical frequencies cannot be known by the agents. First, they cannot observe the actions of all agents at all points in time in a network setting. So instead, in decentralized fictitious play, what we have is agents form beliefs about the empirical frequency or histograms of others. Here I have the superscript I to denote the agent I's belief on agent J's strategy or empirical frequency. And agents are going to form beliefs about the environment as well. So the update mechanism or the algorithm is exactly have these 3 steps. So there's going to be an inertial best response, which means agents are going to take the action that maximizes their expected utility, given these beliefs that they've formed, with some probability 1 minus rho. With probability rho, they're going to stick to their previous actions. And after taking their best action, agents are going to update their local empirical frequency, so FIT, which agent I knows, and it's going to share its belief about others and including itself, everyone's strategy to its neighbors. Okay, so after sharing this belief, agents are going to do a weighted averaging of the beliefs. What this means is here, agent I here keeps a tab on the agent J's empirical frequency, denoted by FIJT. The weighted update is suppose agent K sends its belief about agent J's empirical frequency to agent I. So it's denoted here. Neither agent K or I are connected to J, but K can have beliefs and will send its beliefs to agent I if it's connected to it. And agent I is going to weight this by some constant between 0 and 1, and it will include its past belief about it as well, and it's going to form its new belief. Okay, so these 3 steps are cycled together, cycled through for this algorithm, and it's a synchronous algorithm. Okay, so this algorithm is along the class of action-based learning algorithms in games that have been studied in these vastly, and also along the lines of distributed convex optimization algorithms. So if you cannot compute the term that you need, you keep beliefs on it, and then you exchange information about this. And here they were doing it for empirical frequencies of other agents. Okay. So our first result on this is going to be, and I won't dwell too much on it because this is just an exemplary result that we'll see again. So our first result is if agents are playing there according to this strategy, and in any potential game which means that there exists a potential function that captures the incentives of all agents, And if agents' beliefs about the environment is asymptotically weakly agree, then and there exists a communication network that is that could be time varying, but it's connected. If you take the union of edges over a finite horizon, then the actions of individuals will converge to a pure strategy-Nash equilibrium almost surely in finite time. So I won't dwell too much on this result, but what this means is that agents are taking actions with respect to DFP, decentralized fictitious play, and at some point in finite time, actually not infinity, they'll reach an action profile that is equal to the Nash equilibrium of the actual or the potential game that they're playing. Okay, so in the task assignment game, any covering is a Nash equilibrium. All right, here there was one caveat I noted: each agent communicates its estimates to all its neighbors at each time step, and this may not be desirable, especially when communication at each step is costly. So there could be energy costs to individuals, or there could be limited bandwidth. Or communication may simply be subject to failures, so it may not be possible to communicate at each point in time, even if agents have the energy and the bandwidth exists. So there exists efficient communication protocols in distributed optimization, one-bit communication, communication censoring, which are known to slow down convergence but reduce communication overhead. So here we'll be first agnostic to specific type of communication protocol. We'll provide a general condition for the communication protocol you can design needs to satisfy for convergence of the decentralized fictitious play. And based on this, after showing the convergence of this decentralized fictitious play, we'll provide first and second order belief-based communication protocols, okay? And the setup we'll have is going to work for random communication networks. What that means is there's going to be a potential chance of communication between all pairs of the agents, but there's going to be a chance of failure of that communication attempt. And we denote that by a Bernoulli random variable. So DFP with voluntary communication would mean that agents are going to best respond with inertia as before. There will be some communication protocol which determines who sends messages to whom. And then there will be a belief update after these messages are exchanged. Okay. What is our condition? As I said, we'll be agnostic to a specific communication protocol. The condition that any protocol needs to satisfy for convergence is going to be if an action by an agent is repeated for finite time, agents will learn that action with positive probability. Okay, so this is a really not a strict condition, right? So if we assume the environment is static, then our learning protocol, whatever agents implement, should be able to learn what the static action is in finite time. That's what the condition is saying. Given this condition, we'll show convergence in the class of weakly-acyclic games. Of course, our convergence results are not going to hold for that specific task assignment game. It will be for a broader class of games. And this class of weakly-acyclic games contains the potential class of potential games and congestion games. And the task assignment game is a congestion game. So what does weakly-acyclic game mean? It means that there exists a best response path. So single improvements by single individual at each point in time that will end up at pure Nash equilibrium starting from any action profile. Okay, so that's the definition of weakly-acyclic game. Again, that captures the potential game, that includes the potential games as part of it. Okay, so given this, given the prediction convergence under static environments condition is satisfied, the decentralized fictitious play algorithm with voluntary communication will converge to a pure Nash equilibrium of any weakly-acyclic game almost surely in finite time. So this end part of the result is exactly the same as the result we've shown. But now we generalized it to this: as long as this condition is satisfied, it's going to hold. This convergence is going to hold. Okay, so what's the proof idea? And I'll briefly describe this. The idea of the proof revolves around showing that if you consider a Markov chain where the states of the Markov chain are the actions that agents act with respect to, so the action profiles, then the process of DFP is going to generate an absorbing Markov chain where the absorbing states are the rational actions or the Nash equilibrium action profiles. So we need to show that there's a positive chance of transitioning to these absorbing states, which are the Nash equilibria, and we're done with the convergence. So one implication of the condition that we enforce the prediction converges under static environments is that if an action profile is repeated for t time steps, for t being a finite but large enough number, then agents are going to, their best response actions are going to be equivalent to as if they know the action that is being played. Okay, so here's just a pictorial perspective view of this. Suppose the action A profile BBBA is being repeated after some time t for capital T times, then the estimated best response for all agents is going to equal to the best response to the actual action profile BBBA. Okay, so that's what this means. So our next result is going to show that our we need this intermediate lemma to show the whole proof, that there is a positive probability of reaching a Nash equilibrium A star starting from any point in time. And for this, we use this former implication I've mentioned in the previous slide and the definition of Weakly-acyclic games, where we can transition to a Nash equilibrium action profile starting from any action in finite hops. So suppose BABA is the action profile we start at time t. We know BBBA is the Nash equilibrium where no individual has a unilateral deviation, profitable unilateral deviation. So suppose BABA is being played for finite amount of time, long enough, capital T, for agents to realize that's what other agents are playing, that's the action profile being played. At that point in time, we can have agent 2 best respond and all the other agents stick to their previous actions because of the inertia, the likelihood of sticking to their previous action rho. Then if agent 2 is going to transition to action B because that's going to be the profitable action, then we reach the Nash equilibrium with this sequence. And this sequence has a positive probability, and you can construct such sequences for any action profile you start up with to reach a Nash equilibrium action profile. Okay. The next result we need is once you get to Nash equilibrium, you won't leave that. Okay. So again, the idea is you can, let's see, we reach action profile BBBA, which is the Nash equilibrium. Then if you continue with this action profile for finite number of steps, long enough though, then agents will know the action that is being played and they will never switch because that's the most profitable action that is being played. So combining these two lemmas, we establish that we can reach these absorbing states and they will be reached in finite time because it's an absorbing Markov chain. Okay. So obviously, this result relied on this condition that we have this prediction on guarantee under finite, under static environments. So based on this condition, we can generate novel communication protocols that satisfy this condition. So the communication protocols we will specifically talk about will rely on two metrics: novelty of information and belief mismatch. So novelty of information answers the question whether agent I has something new to say or share with the world. Belief mismatch answers the question whether agent J needs the new information that agent I is willing to share. Okay, so what is the gap between the belief that agent J has and what is the actual action or empirical frequency that agent I is playing with respect to? Okay, so based on this, you can have this communication censoring protocol like an optimization where agent I attempts to send empirical frequency its information to all agents if it has something novel to say. So if HIIT is greater than eta 1. Another communication protocol that you can come up with is based on novelty and belief mismatch, where agent I is going to share its signals or estimates with agent J if it has something novel to say, and if agent J, there's a big mismatch between agent J's belief and agent I's actual belief. Okay, so this belief mismatch allows you to rank neighbors to communicate, and all of these conditions are going to be threshold-based communication protocols. You can also add limited bandwidth communication, which means that agent I doesn't share all its distribution or all its empirical frequency, but just sends the leading action and its frequency. And you can come up with different combinations of these protocols that I laid out. All of them will satisfy this, our condition that we need for convergence. Okay, so let's see these protocols in action in a set of numerical, in a numerical setup. Again, our setup is the same, so I won't describe it again. We have the task assignment problem. That's our running example. But now we will assume that agents will lose connectivity as they move away from each other. So the likelihood of successful communication will fade with exponentially as they move away from each other. And we will allow here, one tweak we'll add is we will allow agents to determine how much they would like to communicate with the agent, so they can tamper with the routing rate. And we'll also have a tweak or another flavor of this algorithm where we'll include communication-aware mobility. So mobility is optimized, so agents just don't move to their selected targets, but they move toward targets, but also account for the fact that if they move too far away from the team, they may lose connectivity. Okay, so here on the left, with a particular choice of these parameters of censoring, mismatch, fading, and inertia, you see that red, blue, and green on the left is the convergence of two equilibria of the action profiles or the empirical frequencies. So all of them have relatively the same rate. Again, the red is the mobility-aware communication protocol. The CDFP is the voluntary communication, DFP with voluntary communication. The green is our standard DFP, where agents attempt to communicate at all points in time. So you can see the average communication attempt significantly dropping for blue and red, while the green is the same. So agents attempt to communicate all times. So let's compare the estimation error. So how is the mismatch, belief mismatch evolving over time? The left is the same, distance to equilibrium, convergence to equilibrium is the same. The right shows that the green over time is the constant communication attempt is going to achieve a better estimation error, obviously, because the communication continues. But the blue and red are doing well at the beginning, and that's just enough to achieve convergence, actually. And here we showed on the right, again, the communication rate, the successful communication attempts. So you can see the mobility-aware communication is achieving a higher success rate in communication attempts, simply because agents stick together for a while. And it's easy to see here when we plot the points that agents move around, how agents move around. So the right is the standard DFP algorithm, where you see zigzags happening, where on here you see the agents sticking together until they resolve their differences of where each agent is actually selecting, which target they're selecting, and then they move away from each other. Okay, so up until this point, we assumed there was uncertainty about the environment that's disappeared over time, right? So agents resolve their differences about the target locations that they were given. Next, I'll visit the issue on persisting uncertainty and describe our approach for convergence using the framework of near potential games for decentralized fictitious play. So the question we're interested in is, what happens to best response type updates when agents cannot resolve their differences in the state of the environment? So agents cannot resolve where each target is. So they feel they're closer to that target, but one of them is actually more closer, right? And this can arise because agents stop receiving signals or stop communicating with each other. So what can we say when agents cannot agree on the objective they're given? So when consensus is not really possible. So the premise here will make use of the framework of near potential games, which defines any game with respect to its closeness to the nearest potential game. And the premise of our approach is, if agents are playing a potential game and they disagree on the environment variable, like the target's locations, then the game they play is the near potential game. with the nearest potential gain being the potential gain given the correct value of the environment variable. So to define the nearest potential gains, we need to define a distance metric between two games, gamma and gamma hat or gamma prime. For this, we'll use maximum pairwise difference, which is based on the difference in players' payoffs resulting from unilateral changes. So we look at all possible unilateral changes and the associated changes in payoffs in games gamma and gamma hat. And we take the maximum difference between them as the distance between games gamma and gamma prime. So this is the formulation, and that's what it means in words. Okay. Then a game is a delta near potential game if there exists a potential game with delta distance to that game. So in general, one has to solve an optimization problem to find the closest potential game. Here, we're going to assume we know the closest potential game, or the nearest potential game is known, and we focus on the properties of learning dynamics in these delta near potential games. Okay, so here we'll consider a slight modification to the decentralized fictitious play algorithm, where we'll have constant communication attempts, but you can have voluntary communication attempts as well. But here, for simplicity, we'll have constant communication attempts. And the updates will not involve any inertia, so agents will just best respond, not with any probabilistic way. They'll just best respond at each time, okay? So more importantly, you don't see any environment variable in the utility computation because it's implicitly, the uncertainty will be implicit in our near potential gain framework, okay? So given the DFP algorithm that I mentioned above, we have the following result for near potential games with time varying networks. So we have a delta near potential game where the potential function of the closest potential game is given by U, shown here in red. We suppose a time varying communication network that satisfies bounded communication interval. So union of edges over a finite horizon is a strongly connected network. Given these assumptions, we have a lower bound on the change in potential function as shown here. So what this says is that the change in potential function value from time to t to t plus 1 is lower bounded by these two terms. So if you look at the first term, right? So the second term is diminishing in time faster than the first term. And the first term is positive when epsilon, right? If the empirical frequencies are epsilon away from Nash equilibrium, then the first term is positive if epsilon is larger than n delta, right? Delta is the delta near potential gain, comes from there. So using this result, you can show that the potential function values are improving until we get to near a Nash equilibrium. Okay, so the empirical frequencies will obtain potential function values that are comparable to rational behavior. That's what this result implies. Okay, so just to show this in the target assignment game and how these results play out for when there's this uncertainty around the target locations. So here we assume agents receive location information of the targets for finite time, and that these signals stop, right? So agents do not reach consensus on where the targets are. So when the beliefs about the environment are close, we have a near potential gain. And in this setting, we find that agents actually reach the exact Nash equilibrium of the closest potential gain. And this convergence is faster in ring network in star network compared to a ring network. Okay, so in this last part, we briefly considered agents disagreeing on a common payoff relevant state of the environment. We analyzed the performance of the DFP in the framework of near potential games, and then we translated these results to settings where there's persistent disagreement about the state of the world. So together, these two results push toward designing decentralized learning algorithms for network multi-agent systems that operate in unknown environments. So just to conclude, this work is mostly due to my graduate student Sarper, and he continues some of the prior research directions I've been pursuing with the help of my collaborators listed here. And last but not the least, the research is partially supported by a grant from NSF. With that, I'll stop and I'd be happy to take any questions you may have.
Okay, thank you very much, Ceyhun. Give this a three-part presentation on the decentralized learning algorithm. I was wondering, you know, I'm hearing about this new phrase, federated learning model also recently. How is this related to that expression?
So in federated learning, the goal is you have a star network structure where each agents, there are multiple workers, and there's a centralized processor that keeps the model that that we care about, but it's a statistical learning problem, right? And the federated learning parallelizes the learning and limits the information exchange between the workers and the data, local data, and the centralized processor, where each local node keeps its own model, its own data to itself, and operates on the model that central node sends it. So it's so I think the closest framework that I would think of that this would be related to is more computation or distributed learning at the edge, right? So where you have these connected set of nodes, instead of communicating with a center, they all have their own information. The tweak we add here with game theory is that while our model's behavior or performance is going to depend on what your model is, what other workers' models are. So that's where the strategic learning and thinking comes in play. It's not just a statistical learning framework. If you recall one of the first slides I showed, agent one has to think what others are going to think about this environment, not just the environment, but about each other. So that's where the game theory comes in. And it's, so I would say in short, federated learning is a particular structure that we use for learning at the edge.
Well, that's a very nice explanation. Thank you very much. Any questions from the audience?
And I think Sarper is in the audience, so he can answer the questions better.
Yes, I'm here. Thank you.
Okay.
Hi, I do have just one question. I might have missed it.
Go ahead.
So the initialization, when you said that, for example, in the example of the targets, when the targets are not known, I'm confused as what is the first set of actions based on what? Is it random?
It's random, right? So it could be, well, so there's one constraint that we need where the actions, it could be random, but our empirical frequency, our initial beliefs has to agree, so that this weighted averaging converges to the right one, right consensus. But it could be random, right? You have an initial belief, and then you compute your expected utilities with respect to this initial belief prior. And you take the action that maximizes your expected utility with respect to that. So the first action could be random, or the first belief is essentially you can base it on the initial belief that you have. Does it clarify?
It does.
So we're free to choose whatever action you want initially.
Do you anticipate that the converges would be impacted by specific action, initial action? And if so, did you test them?
Yes. Yes. So the convergence result is you converge to a set of possible Nash equilibria here, right? So I just said one. I don't know which one it's going to converge to. And Nash equilibria are known to be suboptimal. So which one it will converge to? Some of them can be suboptimal. So which one it will converge to depends on this Markov chain we're constructing essentially. And we don't know which absorbing state it will reach. You can do some analysis of which is more likely, but it's hard to do, and we haven't done it.
All right, thank you very much.
Any other questions? So Ceyhun, if you don't mind me asking another question, probably slides 29, you mentioned about the estimation ability, estimation accuracy.
Here or this one?
Probably 30.
Yeah, this one. This one. So this. Okay. Okay, this one. So this is the estimation error that you have on the right.
So it looks like makes sense, right? You kind of get down to a certain level, it kind of plateau over there. You know, in the centralized estimation, there's a lot of studies. There are all kind of different lower bound, like the most famous probably the Kramer law.
Yeah.
And do you have a sense of in your kind of distributed learning type of environment? Do you have any kind of this limit, you know, where it goes, and how does that kind of factor in that kind of situation?
Yeah, actually, I gave one proof result. Another one, which I haven't talked about, depends on how fast this estimation error shrinks to zero when there's constant communication. So we have a rate on that, and that's based on the rate of convergence of this updates and the consensus updates combined. So remember, they're doing weighted averaging, so it's a form of consensus. So actually this rate in green is going to follow log t over t square. So we have a rate on that, but we don't have a rate on this communication protocols when these voluntary communication protocols are implemented. So that's why we went the other convergence path, not the rate, because when you get the rate, you can show actually when the estimation errors get close to each other or get close to zero, then it's as if you know what game you're playing, and that's how you show the result through continuity arguments. So for green, we know it's going to go to zero because there will be constant communication attempts at rate log t over t square.
But even with other kind of noises in the environment, you still can go to zero?
Yeah, good question. So the fading, if there's fading, then you won't be able to achieve it. That result holds when there's no fading and the probability of communication failure is fixed or it's equal to 1.
I see. Okay, that makes sense. Any other questions? I think we are 5 minutes past the set time, but we are still within the hour. Okay, if no other questions, let's give a round of applause to our speaker, and thank you very much, Ceyhun.
Thanks.
And I wish you all very good Labor Day. Thank you.
All right, thank you.